So hello everybody. So first of all, thank you very much for the invitation to give this talk, this short presentation. So I am Fabrice Requier, a French researcher, and I work south of Paris. I am an ecologist working on bee conservation and crop pollination, and I did a postdoc on Asian hornets, on the impact of the Asian hornets on beekeeping. So that's why I will present today the result of this postdoc. Okay, here. So this is a very nice website done from it's Quentin Rome, a French researcher, a colleague that did this website. I invite you to visit it. And you have each year this map, this European map with the spread of the Asian hornet over Europe. So that started in 2004. With a single department, a single region, and very quickly the Asian hornet spread over France and finished also to spread in the neighboring countries, starting with Spain, Belgium, but also Italy and Portugal, but also it crosses the Channel to go to the UK. So it's quite alarming. First was alarming for beekeepers because of the action of this variability now on honeybees. So this was also a very good opportunity for researchers to work in collaboration with beekeepers, and starting to understand why first beekeepers were very convinced that the Asian hornet, the predation of the Asian hornet could lead to a collapse, mortality of the beehives or loss of beehives. And so, in collaboration with beekeepers, we started to look for the mechanisms, the processes that could lead to colony collapse. And so we focused on two main drivers that could directly affect the beehives. First was homing failure. So basically the bee foragers are going out to collect nectar and pollen, water, and what else. And they coming back to the beehive. So of course foragers can die outside, but when they come back, the hornet can catch them, and so the foragers the homing behavior is a failure. So this is the predation, the direct impact of the predation, and the second parameter that we focused on is this foraging paralysis. This is a bit more indirect. It's a kind of response of the honeybees to the presence of many hornets in front of the beehives. That's like here you can see the hornets are hovering in front of the beehives. Here we have 5 hornets, and more you have hornets, more you have a probability that the beehive will not forage anymore. You have no exit, no enter-exit, because they block this activity of foraging. So that is what we define as a foraging paralysis. So yeah, it was a kind of discussion with beekeepers, but also based on literature, that we focus on these two parameters that could directly impact the colony dynamic and could lead to colony collapse. So then it was a challenge to assess how to assess this risk of honeybee mortality related to the Asian hornet, but we focused on, we carried out a 5-year experiments in France, observing these two parameters, so the foraging paralysis parameter and homing failure. And yes, we published that two years ago. How we did that? So we monitored 131 beehives in Western France. So you can see in the map here the red points are the beehives that were monitored. For the main objective was to observe the beehive during 17 minutes, observe the in and out activity of the bees, and to count also the number of hornets hovering in front of the beehive. So we did that several times on these beehives, and on the right side you have here the results, the time series of the number of hornet, the maximum number of hornet hovering in the same time in front of the beehive. So just before I'll show you the picture with 5 hornets, but in some times we also observe 20 hornets hovering in front of the beehive, which is huge. Yeah, so this was the first parameter. So we count the maximum number of hornets hovering in front of the beehives and the activity of the bees, in and out activity. And the idea was, based on this data, to compute or to measure the foraging paralysis. So if the hypothesis was more you have hornet hovering, less you have flight activity of bees. Second part, we also carry out camera video surveillance, camera monitoring. So something's more automatic, but less, it's on a single beehive, so it's a less spread spatially. So we use a stereo vision camera to have a 3D measure of the flights of bees and hornets. We could also differentiate hornets and bee flights based on the size of the track. So we recorded during 10 days. We recorded more than 600,000 trajectories, so flights, behavior of flights of bees and hornets. And we also, big idea, the main idea was to record successful predation events. So we recorded 126 successful predation events. So this idea was to compute then the homing failure, so the probability for foragers that when the forager come back to the hive, the probability that they can come back, or if they just be catched by hornets. Okay, so we have now the two parameters. So we did some statistics. I like statistics, so sorry, but I will show a lot of statistics. So on the left, you have the results based on field work. You have the result of the homing failure. So of course, I can't see very well. Yes, so here you have the number of flights, so the flight activity, and here you have the foraging homing failure. So basically, you have a higher probability to be catch when you have less bees flying, so less traffic. So this was also assumed before. And on the right side, you have the foraging paralysis, and of course, when you have more hornet hovering in front of the beehive, more you have a foraging paralysis, so less activity. So this was more or less evident, but very interesting to extract these two parameters, these two statistics, so the slope and also the parameters from this field data to then compute in a model that Pete knows very well, so the behave model. We use this behave model then to see if these two parameters, so the paralysis syndrome and the homing failure, can affect the probability of a colony to survive during the winter, or if there is no problem. So it's a theoretical approach based on simulations. So we use this behave model. We run about 1,000 simulation with very simple calibration. And we implemented these two parameters, so the foraging mortality rates, the increase of the foraging mortality rate, and for the foraging paralysis, we changed the quantity of flights the colony can do during a day. And we only focused on the period of hornet activity, so in autumn. And what we can see, so we have two different colors here over the year. So in blue you have the colonies, so the simulations that were successful, so without any collapse, and in red you have the colonies that collapsed, so the prediction of colony mortality due to the implementation of these Asian hornet impacts. So this is quite interesting because we can see different patterns, so different groups of red lines. First you have these red lines that go upper, and you have red lines that go just below the successful colonies. So this was also interesting, and then I look for why we have different patterns, and how these two parameters, so the foraging paralysis and the homing failure, affects the mechanism of the colony. So don't worry, I will explain this slide. This is kind of a mechanism. So you have here the hornets. So hornet load means the quantity of hornets hovering in front of the beehive. And this could affect in the model or mechanically the colony on different parameters or colony traits. Could affect directly the adult population size, or indirectly could also affect the pollen storage, because yes, the foragers are collecting pollen and larval population. So this is a lot of statistics, but I will focus on these main results. Here you have, when you have hornet loads below 13 hornets, this was a threshold we used. We observed in the field work that 13 hornets was the threshold. Below 13, we have still flight activity of the bees. When we have more than 13 hornets, the colony just stops the flight activity, and so we have a foraging paralysis. So here it's the impact of these hornets with a load of below 13 hornets. And the impact is that, yes, the hornet can reduce the adult population size due to predation, and this population size predicts the probability of the colony to survive. So if you have very small quantity of bees in the beehive, you have a higher probability to collapse. So this explains this part of the curve, the red curve. So all the simulations that were small co-colonies with a small population size collapsed because of hornet predation, so the homing failure, direct predation of adult bees. The second scenario is very more interesting for me. It's when we have a lot of hornets, so more than 13 hornets hovering in front of the beehive. So we are in the situation of foraging paralysis. What we observe is that we have another processes, another mechanism. The hornets then, in this case, affect negatively the quantity of honey reserve in the colony, and this honey reserve is a predictor of the colony survival. That means, so we have no predation, it's just foraging paralysis, so all the population that did not fly to forage consume the honey reserve much more than if they forage. And so the colony, before wintering, they are consuming all the reserve prepared for the winter. So it's typically a starvation. And this is all the cases, all the colonies here, the red curve that are with a lot of honeybees is exactly that. So we have a bigger adult population because they are not flying, but they are consuming a lot of honey, so they collapse just during the winter due to starvation. So yes, this was quite interesting to go deeper in the processes. And then we also we were interested. Okay, now we know the two risk of colony collapse. So you have homing failure. So it's small colonies, for small colonies, honeybee colonies, and you have foraging paralysis for the big colonies. So how to help the beekeepers to reduce this risk of colony collapse? Here it's a synthesis of the main method for controlling the ASEAN hornet impacts. And you have, yes, different parameters that are established, so the costs, the environmental impacts, and the scales of the action. And we focused on the first one because it was an easy method to run in the fields, and also because it was a biodiversity-friendly techniques, so that doesn't impact the native entomofauna. That was a big aim of our study, second study. So what we do, we tried to test if these muzzles, I will show you then a picture, can be a method that we can recommend to beekeepers to control the ASEAN hornet impacts on honeybee colony mortality. And not on the predation, but just to maintain the livestock for beekeepers, so that they cannot lose any more beehives. So what we do, we in France, we did all the experiment in France. Again, we did a lot of experiment in Western France in a network of beekeepers, and we installed pairs of, not pairs, but we selected two beehives. One was equipped with this muzzle, so you have a picture here. It's a gride that allows the bees flying through the grides, but the hornet cannot go close to the beehive entrance. So one colony was equipped with this muzzle, and the second colony was the control, so without the muzzle. And we compared, as I presented before, we measure with observations the number of hornets hovering in front of the beehive, the number of bees going out of the colony and entering in the colony, so to measure the foraging paralysis. And we also observed the number of hornets that successfully catch a bee, predate bees. So this was a lot of field work done by a colleague, so Quentin Rome, during several years. And the results are here, so it's the same graph than before, focusing on these two parameters, homing failure. So what we here the foraging paradises, you have two colors. In red, you have the colony with the muzzle, and in gray, you have the colony without the muzzle. What we observe that the presence of this muzzle doesn't affect the predation of the hornet on bees. So this was also totally normal because it's just a guide, so the hornet can catch the bees when they want. But this is a second result, more interesting. The presence of this muzzle reduces the foraging paradise activity. This was the idea of the muzzle. So this guide, it's a guide that is about 20 centimeters at distance of the beehive entrance. This guide allows to maintain the flight activity of the colony, even if the hornets are present, and are present with a very high number of hornets. So here we have some colonies with 20 hornets flying. So this was quite good because the presence of the muzzle reduced the probability of foraging paradises. Then again, I did some simulation using Behave to implementing these two parameters, and with the control, one simulation with the control, and one simulation, one set of simulation with the muzzle simulated beehives. And here you have the results. So this is if you have a muzzle, the probability that you increase the survival of the colony. So if you have very few hornets, you have no effect. The muzzle is not useful. But if you are in the situation with a lot of hornets, the presence of this muzzle could significantly reduce the risk of colony collapse. So we could recommend beekeepers using muzzle in this case to reduce colony losses due to hornets. So it was very useful. It was a kind of second part, more technical for beekeepers, and a kind of recommendation. Now in France, we have a lot of beekeepers that are using or trying to develop this technique using different guides, the side of the guide. So they are developing that, and they enjoy to develop that. And the big points and positive points, it's a fully biodiversity-friendly technique, so we don't touch the entomofauna. So this was very useful. Another point we also based on this project, is kind of baby of the first project. We were also interested to estimate the economic costs related to the colony losses due to Asian hornets. So we focused on that. Okay, so beekeepers can lose colonies because of hornet predation. So we have now some estimates based on simulation estimates of how many colonies they can lose. So we did this kind of procedure to compute at national scale in France, to compute for each region, each department in France, based on the number of hornet presence, hornet nest presence, based on the number of beehive present per department, per region. We computed the probability to the probability of beehive mortality. And then, based on this probability, we estimated the cost, economic cost, so the cost to replace the colony that died. So we developed these processes based on national scale data sets. So the first data set on the right, on the left side in blue, so it's the prediction of Asian hornet nest density. So for each pixel, it's not a pixel, it's a municipality in English. For each municipality, we predicted the presence of this Asian hornet nests. Of course, it's based on nest search program that you can see here in black points. So it's also done by Quentin Rom again. Did a lot of field work, and so he explored different municipalities and searched for all the nests during autumn when it's easy to observe. And then we computed with another colleague, Alice, we computed this extrapolation at national scale. In green, you have open data in France. It's the quantity of beehives managed by beekeepers in each municipality. So we have the predators, we have the prey, and I simulated for each municipality the probability to have colony losses due to hornets. And here are the results. It's quite short because it's very big estimation. So it's I'm an ecologist, so it's a very big estimation. So it's to have an overview of the potential economic costs, but it's not the reality when we are in the field. It's a big estimation, and we estimated that. In France, about 30% of the beehive could be lost due to Asian hornets, and these losses could lead to 30 million euros per year due to colony loss. So this is a cost to replace the colonies that died due to the Asian hornets. In the graph below, you have this all the French regions, and you have, of course, a lot of a huge variability per region. In south of France, in Corsica, for example, the impact is much lower than in Occitanie. Occitanie is a region where the hornet was introduced originally. And on the right side, you have the economic impacts. This was interesting also to compute. So I compare the costs of the hornet, so the cost to replace the colonies that died, with the honey production that the beekeeper have in each region. And you have a percentage, so if you have 100%, it means that the cost to replace the colony lost is equal to the production of honey for the beekeeper. So it's not sustainable anymore. And so, of course, we have some variability per region, but it was surprising to see that Occitanie, where it's the regions more impacted by economically by the hornets, is not the region that is more impacted economically for the beekeepers, because the production of honey is much higher than in Normandy. No, Normandy it's northwestern of France, where the beekeepers they did not produce the same quantity of honey, so the impact for them is much higher. And overall, we are talking about 25% of the production could be used to replace the colonies that are died due to the Asian hornets, which is not negligible. It's a huge impact. I don't know if I have still time, but I have a less study to present. A bit different, but I think it's a good conclusion. Okay, here we have, we produced some science-based estimates. Of course, we did this experiment in the field in collaboration with beekeepers, but usually when we are talking with biological invasion, beekeepers in France, they want to act rapidly, and usually science is very long in terms of producing recommendation and assessing the impact of species. So we are in a situation where we are disconnected between the needs of action from stakeholders in the field and the production of recommendation from science. So how to do? And the idea of this last study was, okay, so in France, the beekeepers, they did action during about 15 years without any strong assessment of the impact of the hornet. So they did a lot of things, and they also have a perception of the risk that is based on their own observation and not based on science assessments. So we compare. The idea was to compare the perception of the beekeepers, or okay, if they think they will lose some colonies, if they think that the hornets, the load of hornet is very high and could lead to colony collapse, and we compare that with our estimates based on protocols for field assessment, but also based on simulation and risk assessments. So what we did this map. So we have in colors here from yellow to red. We have the risk assessment based on our former predictions. Okay, in red you have a high risk of colony mortality. So beekeepers, it's more or less sure that they will have 30% of colony mortality in their apiaries. And in I don't know the color, but in white you have no risk. So of course the hornet is present, but not in such quantity or density that could affect the risk of colony mortality. And we also did a citizen science program. We spread a questionnaire asking beekeepers about their perception of the risk. So if they think the hornet is present, if they think the hornet, no, if they observe the hornet presence, so a nest, if they observe predation, so the risk of predation, and then if they think their colony are directly impacted, the colony mortality is directly linked to the Asian hornets. And we have a last question about if they are doing control techniques, if they applied, for example, trap, they use traps, or they are doing some practices to control the predation. So we published that last year with the colleagues. So again, statistics. Sorry, I will explain briefly. So on the top here, you have the stakeholders, so the beekeepers. So all the beekeepers, if they observe the nest, yes. If they observe the predation, so the action of the hornet predating on their beehive. And if this, they also they assume that yes, they have a huge risk, or their own risk assessment about the predation and the link to the colony mortality, and if they do action. And below you have the same based on the science-based assessments, what I explained before. So okay, the map of the hornet nests, the probability of homing failure and foraging paralysis, the link to colony mortality, and the recommendation. So, okay, in this case, you have to act or not. And what we can see that, okay, the stakeholders or beekeepers, they are connected. Here you have an arrow. They are connected, so you have a good correlation between stakeholder estimation of nest presence and science observation. The same for the predation risk. Okay, the beekeepers observe predation. It's correlated with science-based estimation. But here you have no connection, a disconnection between the perception of the risk of stakeholders and the reality of the risk, not the reality, but the estimation of the risk based on science programs. And also the recommendations are not connected. So they are acting when it's not necessary, or the reverse. They are not acting when it's necessary. So this was quite a huge surprise to see that finally, yes, we were convinced that this was okay. Of course, they are very good to observe, that much better than scientists to observe the beehive and to estimate if there is a predation. But the perception of the risk is not good and is disconnected with also the need to act in the field. More importantly, the last question of the questionnaire was about if they are using traps and different methods to control the Asian hornet. And about 90% of the beekeepers answer yes, they are using traps. So more or less it was half and half using commercial traps and homemade traps. And we also questions what you find in the traps. What is the diversity of, not the diversity, but the main taxa you are observing in your traps. And here you have in the red color, you have the frequency of observation of the Asian hornet. So here it's about 80%, but on homemade traps and homemade baits. And more or less, yes, I are observing all the time Asian hornets in the traps, which is good for them. But they are also observing a lot of local entomofauna in their traps. So, such as dipteras, some dipteras, lepidopteras, and what else, but also the European hornet. So Vespa Fabro. And the same idea, but with another representation, is that okay, they are using a lot of traps. For example, it's a log this. So here it's 2 means it's +1. So 2 means 20. 20 traps used in an apiary. And more they are using traps, more they are successful to catch the Asian hornets. And here we found no correlation, means that even you are using a single trap, you are collecting a lot of local entomofauna, which is not very good, not biodiversity friendly. So the conclusion of this study was, okay, we need more communication between scientists and stakeholders, even if it's much before the strong result of the risk assessments. We have to be more close with the stakeholders in the two-way to improve the sustainability of the action in the field. Okay, so it's all for me. I hope it was interesting. and thank you for your attention.